Yeah, so yeah, sorry for some technical issues that it happens usually. So yeah, so today I'm going to talk. So the goal of this talk is to explain what we did in our recent work with Leonid Rybnikov and Boris Feigin. But most of the time I will spend on just introducing objects and rather than result itself, and then I will just formulate the result. By the way, how much time do I have?
Till 5, so effectively 50 minutes.
Okay. Let me try. So my main hero is what's called usually Bethe algebra. So let me introduce it. So Bethe algebra. What is this? Well, I need to consider GLN, which is all linear transformation of n-dimensional vector space. Consider universal enveloping on it of GLN, and take tensor product or n-fold tensor product of universal enveloping, and my Bethe algebra will be commutative subalgebra that lives inside, and it will depend on some parameters, complex numbers, which I denote here by Z. So Z bar is a sequence of complex numbers, Z1 to Zm. So this lives in Cm. And what is this algebra? Well, I will need, to define it explicitly, I will need what's called standard basis of GLN. So here I and j runs from 1 to n. So this is standard basis, meaning that Eij is matrix with 1 at ith row and jth column, and 0 everywhere else. And then I will need one more piece of notation, is that if I write Eij with upper index a, here a runs from 1 to m, it means that this is an element that lives inside m-fold tensor product of UGLM. And by definition, it is just in any tensor factor is 1, and at eighth tensor factor, it is Eij. So, and then once again, and so on. So this is mth place. Okay. So now I'm going to introduce, for each I and j running from 1 to n, I'm going to introduce an element Lij, which will be differential operator of order 1, actually, or 0. So it is just given by the following formula, delta Ij, and then so derivative with respect to x, so differential operator in parameter x, minus sum over a Eij over x minus Za. So Za are those complex numbers that I fixed in the beginning. So this is for each I and j, and this is some differential operator which takes values in rational functions, which takes values in UGLN tensor n. And so then I need to consider what's called column determinant of, so this is n by n matrix, right? So I rather maybe should take L to be a matrix with elements Lij, so I and j from 1 to n. And then I need to consider column determinant of L. What is this thing? Well, it's just the same, defined in the same way as the determinant. I just need to order my elements there with respect to the second index. So it's sum over all permutations, and then I have L, and then sigma of 1, 1, L sigma of 2, and so on, L sigma of n, n. So I'm just choosing the order such that the second index, which is the column index, grows from the left to the right. And what is this guy? Well, this is actually some also differential operator, but of degree n. So I can expand it like this. Derivative to the power n, and then some coefficients bi of x, dn minus I runs from 1 to n, where bi, they have the following, they're the following. So this of the following thing, some coefficients, some residues over x minus za to the power j, where these elements bij, these are some elements in u gln to the power 10 to the power m, right? So these are some very non-trivial elements, and by definition, Bethe algebra, so they depend on z, of course. So I expand this column determinant, and I get this bij's. And by definition, my Bethe algebra, well, I need to write something like this, depending on z. It's subalgebra here generated by all these elements. Here I runs from 1 to n, j from 1 to I, and a from 1 to n. And this is what's called Bethe algebra of Gaudin model. Well, for the following reason, so I just list some the most important properties of this algebra. So properties of B n of z. Right, so we, first of all, it's commutative. And second, it contains celebrated Gaudin Hamiltonians. That's why it's called the Bethe algebra of Gaudin model. Well, these Gaudin Hamiltonians, let me give a formula for them. I'm sure that a lot of people know that, but nevertheless, it's some. So there are m of them, right, for each index a, and the formula is like that. You need the so-called split Casimir in numerator. So here, sum over b, which are not equal to a, over za minus zb. And so, so you have Gaudin model, which is integrable in the sense that there exists like a big, in some sense, commutative algebra of higher Hamiltonians, right? Where this, which includes this Gaudin Hamiltonians themselves. Okay, and then, well, I need. So this is about some subalgebra, and I'm interested in its action in some representations. So let me consider V lambda. So this is gln module. Well, irreducible, finite dimensional, such that, well, of highest weight lambda. And well, I will be interested in so-called, for now, we're interested in so-called polynomial modules. So those which live in C n tensor K, which automatically means, well, that my weight lambda, which is, well, some complex numbers, lambda 1 all the way to lambda n, well, lambda I should be non-negative integers, and also lambda I is greater than lambda j if I is smaller than j. Well, should be greater or equal here. Okay, and so actually I need to fix well, take tensor product. So my representation of UGLN tensor M that I need, I will denote it like this, V of lambda, and this is a tensor product of M polynomial GLN modules of highest weight, lambda A. And well, my UGLN tensor M, of course, acts on it. And so is Bethe algebra. And well, usually what physicists do after they come up with such algebra, they try to simultaneously diagonalize well, images of the elements of this algebra in the representation. And so let me consider eigenvector. So V is a common eigenvector of my Bethe algebra. And well, it lives in here, V of lambda. And what I can do, I can take my differential operator that was, maybe I introduced this notation, maybe not, but okay, let me just do it now. So this is my column determinant that I started with of this matrix L. And so I can take it and actually consider its image on my eigenvector. So the coefficients of my of this column determinant, I actually well, they if restricted to V, they just become scalars, right? So this is just some differential operator with scalar coefficients. So it's written down as follows. So it's just dx to the power n plus sum over I, j, and a of b, I, j, a over x minus z, a to the power j, and d to the n minus I, right? Where these are just numbers, the small bij. So if I act by this generator of Bethe algebra on V, this is just the same as multiplication by number bij a. And this guy is just complex number. So this is just some differential operator. And we actually can try even to solve the corresponding differential equation. At least hope to solve it as formal series, like at least find formal series solution locally around some point z. So what we can do, we can take some point z in complex plane and well, consider my local coordinate around this point. So I denote u to be x minus z. And then let me consider bi of u. So if I have, so bi of u, it is Laurent series of bi of x at z, right? So this is a series in Q. And what is bi of x? Well, these are just coefficients in front of dn minus I, right? So bi of x here is just sum of j and a, bija over x minus za to the power j. Okay, and so if we consider this Laurent series, I actually can consider a differential operator in U with coefficients which are series in U. I'll write for it as dn of U. So it's d U to the power n plus sum bi of U dn minus I. Right, so here I runs from 1 to n. And well, I can try to find f of u. So goal to find f of u, which is a series in series in u of the following form. Well, it just starts with some power u with some power k, and then I have higher powers of u, so like with some coefficient a, maybe 1, k plus 1, and so on. So I just take this and put in this into my equation dn of u f of u. And so the question is, what do I get? I'll try just to find k, which, well, I will get some equations, which are algebraic equations on k, and my coefficients a1, maybe a2 here, and so on. And, well, if I consider like the smallest degree term in here, this will be some polynomial equation that will give me conditions on k. What I can put here, like a necessary condition for k to even have such solution. And then I can see that if my z is not one of my za, which are single points, then my k can be 0, 1, 2, and so on up to n minus 1. So with this very easy observation, meaning just that if z is not one of these points, this is not single point. But if z is one of them, things become more interesting. And actually, my k is then can be n plus lambda I a minus I, where this lambda I a, so remember I had this tensor product, right? And these are some integral dominant Gillian weights. And so these are actually elements of this weight. So lambda a is lambda a1, and so on, lambda a n. Right. So this is already non-trivial, and I can formulate this as a theorem, which was observation by a number of people. Just to name a few, maybe as should be Frenkel, should be here, which is Edward Frenkel, in his study of relation of Bethe ansatz for Gaudin model and center on critical level, and this originated from his works with Boris Feigin and Nikolai Reshetikhin. And then specifically for GLN, these are my teachers from Indianapolis, Mukhin, Tarasov, and Varchenko. Well, Varchenko not from Indianapolis, but they write a lot of papers together. Okay, so this is one part which is not so hard to see actually. You just need to figure out that your like some coefficients which are they're just central elements, and just compute the central elements on the highest weight vector. It's not so much of it. So much more non-trivial thing is that actually if you have for each such k, you actually have a solution. So solutions f of u exist like a series solution for each such k. And this is, so if you just plug in series like this, you usually do not hope to be able to find all the coefficients ai in it. To be able to solve it, you need to add some terms with logarithms. And so this means that no terms with logarithms are needed. So no terms with logarithms. And people, so this means that, well, some terminology that Dn has no monodromy around ZA. Okay. So this is very important observation. And this is another part of this theorem. And the third part is that actually Dn has regular singularity at infinity, right? Meaning that if you take W to be 1 over X, then you can consider your Dn as a differential operator in W. This will look like dW to the power n plus some coefficients, well, which are series in W. And your AI, so to say, has pole at 0 of order I, right? So the depth of pole grows as I go from the top degree of my differential operator to the constant term. So AI here is a sum, something like this, AIJW to the power j, where j is from negative I, well, so say to infinity. Okay, and so this was a very good observation for people who are studying Bethe ansatz for Gaudin model. And all this actually culminated in proving Bethe ansatz conjecture, well, just reformulated Bethe ansatz conjecture, which is the following thing in modern times. So we actually constructed some map from eigenvalues of Bethe algebra to some differential operators with these three properties that I mentioned. So diff op. So so the set of all such differential operators with these properties, let me just denote it by diff op n, and it will depend on parameters z and lambda. And actually, So this map is, if you restrict, well, eigenvalues or eigenvectors, I would rather write here eigenvectors. So if I restrict it to some particular eigenvectors, this is actually bijection. So I actually need to consider not V of Z, but rather singular vectors, which means that these are vectors killed by Eij with I less than J. And so then theorem, which can be called Bethe ansatz theorem, it says that L restricted to V singular, so to say, so singular vectors of single eigenvectors. So actually, my Bn actually commutes with the action of GLN, so it can be restricted to single vectors, is a bijection. Okay, so this is the story about GLN that I wanted to talk about. Now I will go to to the super case. What's the difference? So do you have any questions so far? Or can you at least say something, because I don't hear anybody, so maybe I'm just talking to myself. So any questions? Let me see that I'm still.
No, what I tell you is very clear.
Okay, very good. I just don't want a situation when something is wrong with internet. I'm just talking with myself, so I checked. Very good. So now let us go and see what's the and this is very big success in the study of Gaudin model and quantum integrable systems, and actually it resulted in proving some conjectures from algebraic geometry, like Shapiro conjecture. And this is a very interesting story, like my favorite one, because and so. But now the question is, let us go from GLN to GLN Lie superalgebra, GLN n prime. Okay, what is this? Well, as a vector space, GLN n prime is just GLN plus n prime, so S vector space. And so it has the same standard basis as GLN plus n prime, but on this vector space we have different structure, which is not a Lie bracket, but Lie super bracket. It satisfies different axioms like Lie, like super Jacobi identity. So you need to put super everywhere. Namely, well, I need to introduce this notation, I bar. What is this? So I runs from 1 to n plus n prime, and so this is 0, right? So this is an element in Z2, I'm thinking of. So this is 0 if my I is from 1 to n. So this is corresponds to the even element. And this is 1 if my I goes from n plus 1 to n plus n prime. Very well. And so this is just notation. And then I have standard basis in GLN plus n prime. And to each element of the standard basis, I would like to assign what's called degree. So this is just, it's an element again in Z2, and this is just I plus J bar. In other words, schematically is just like that, right? Everything which is, so this is n by n block. This is, well, n prime, this is n prime. So everything that is in here corresponds to 0, this corresponds to 1. Okay, and so then I call elements of GLN n prime homogeneous if they are linear linear combinations of EIJs with the same degree. And for homogeneous, so if I have A and B homogeneous, then I can define super bracket, which is just given by well, supercommutator, right? Namely, it's AB minus -1 degree of A times degree of B, BA. And so since I take homogeneous, it's clear what is degree of A and degree of B. Okay, and then I can consider universal enveloping of GLN n prime. What is this? It's an associative algebra, which is just quotient of the tensor algebra, right? Which is just sum over all GLN n prime tensor K. This K goes from 0 to infinity. So by relations, which which are pretty natural, right? I just say that supercommutator in UGLN minus -1 to the degree A degree B BA equals to AB. Well, this is some associative algebra. It's different from UGLN plus n prime, and as before, I would like to take its mth tensor power, and I can actually construct Lie algebra of Dn n prime, which lives inside here, and it also depends on Z, which are m parameters. Okay, so to construct this Bethe algebra inside UGLN n prime, I need instead of column determinant, I need what's called Berezinian. And for Berezinian, I need to invert my matrix L somehow. And to invert my matrix L, I need to introduce so-called pseudo-differential operators. So if I have an associative algebra, and if I have some derivation from A to A, derivation, I actually can fix some T, any complex number T, and then I can define what is a pseudo-differential operator of order T. Okay, this is just a formal series of this sort. So this is D. So this is D to the power T minus I, I sum over I from 0 to infinity. So this just, you look at this, just symbols for now, and these are some elements in your associative algebra. So infinite series like that, and since I said so for order T, I would like A0 to be not 0. Okay. What's the use of this? I can make this to be an algebra. I can try to multiply them as series. I just need to define what is d, this symbol d to some complex power s, and then a. So I need to know how to commute these things. Then I can multiply this as series. So if I commute this, so I just define this, that this is the following element, s minus 1, so on s minus I plus 1 over I factorial, I from 0 to infinity. And here I have a I d s minus I. So this ai is just, I take my element a and act by my derivation I times. So I apply it, and so therefore this is something that lives in a. And so I just define and then can multiply this as series. So my pseudo-differential operators, which I denote like this, on A becomes an algebra. And by the way, it's associative algebra. You can check it using some, some elementary combinatorial identities. It's a good exercise, anyways. Okay, so then I can consider Lij, which is, as before, this is something like this. I just need to put additional sign. So delta ij, derivative with respect to x minus, and here is the sign, negative 1 to the power I bar. And here I have to put sum over a from 1 to m, eij a, which is defined similar to GLN case, over x minus z a. And then if I take, if I consider this matrix, I can actually, it is inversible if I look at the elements as pseudo-differential operators. So L inverse ij, this live in pseudo-differential operators where of in U, GL, N prime, well, rational function, U, GL, N prime, tensor M value to rational functions of X and pseudo-differential operators on such associative algebra. Okay, so now since we know how to invert this matrix, let me take L and consider its n by n submatrix that lives here, and let's denote it as L0. And let me take L inverse and consider its n prime by n prime submatrix that lives in the other corner, and let's denote it as L inverse 1, or maybe 0 bar and 1 bar here. And then I define Berezinian of L to be column determinant of L0 times row determinant of L1 inverse. And then again, I can expand it. Now it becomes pseudo-differential operator of order n minus n prime next, plus, so it will have infinite number of terms, I from 1 to infinity, bi of x, d n minus n prime minus I x. And so then you expand this as rational functions, you get some bij's. You have much more of them since I runs from 1 to infinity now. And then you actually generate by it Bethe subalgebra of super Gaudin model that depends on Z. And this is actually commutative, not super commutative. Commutative inside, well, UGLN and prime tensor N. Okay, so the same construction, we did pseudo-differential operators and Berezinian. Okay, and then we would like to take, consider representation theory, some basic representation theory of GLN and prime. And well, let me take V lambda to be GLN prime module of highest weight lambda. Well, lambda is now has, well, a sequence of n plus n prime numbers. Well, I would like, again, this V lambda to be polynomial, so I would like it to live in Cn plus n prime tensor k for some k. And this actually gives me some condition, again, on my lambda. Well, of course, I would like lambda I to be non-negative integers, but an interesting condition is that if I try to do the following, I can first draw a row of boxes of lambda 1 boxes, and then draw a row of lambda 2 boxes, and then continue until I get to lambda n. So this is n. And then I start actually drawing not columns, but not rows, but columns. And so then I get a column of length lambda n plus 1, and then column of length lambda n plus 2, and so on. And so what I get, so the condition is the accumulation of boxes that I get is actually a Young diagram. So the shape, the outer shape, gives me Young diagram. And this is a condition for the polynomial module of GLN and prime. And so I take this V lambda. So you see the message here is that the same universal object, Young diagram, gives me highest weight of a representation for usual GLN, if n is big enough, and for GLN and prime for Lie superalgebra, right? So my Young diagram is actually something universal that gives, in different ways, highest weights of representations. And so again, as before, my V algebra acts on V lambda. Well, this is some tensor product of polynomial modules. And we are interested in taking our universal generating pseudo-differential operator that was Berezinian of L, and look at its image under restricting to eigenvalue V, eigenvector V, so eigenvector. Well, this becomes some pseudo-differential operators with just coefficients which are usual rational functions in X, right? Well, let me denote it as dn n prime. And well, the theorem here is that if V is given by Bethe ansatz, then my dn n prime is actually rational pseudo-differential operator. So it's d0 times d1 inverse. So where D0 is usual differential operator of order n with z with, well, it's no has all these properties that I listed for GLN, right? It has singular points at z at infinity regular singular point, and well, my exponents at this singular points are given by partition by this sequence of partitions. So but here I need to specify. So this corresponds to lambda. So lambda n. Maybe I should. Right. So this is some part of lambda, right? And D1, the differential operators, lives in, well, it is inside. Lives in differential operators of order n prime with the same singular points, and here exponents are given by another part of my lambda, right? So my lambda, so lambda n, right, means that well, I just
Sorry,
take.
should it be n prime in the previous line?
Yes. This is n prime. Right. So actually, what I'm doing, I'm lost in my notation, but long story short is that, well, I have this lambda a, right? It is what is given at around point ZA. So this is something like lambda 1, blah, 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 lambda n, and then lambda n plus 1, blah, 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 lambda n plus n prime, right? So I take this piece, and this gives me lambda n, right? Well, a. And bar means that I can see the sequence when for each, well, I combine all a's together. And then lambda n prime, well, this is not the last part, but rather this one, negative lambda n plus n prime, then negative lambda. Well, these are some technicalities, but I don't want to lie too much to you. So like this. Okay, so Bethe ansatz for super caves gives you that your corresponding describes your eigenvectors through pseudo-differential operators, which are ratios of two differential operators, and you know analytic properties of numerator and denominator. Right. So this is known. What's not known is, can we have, so question, do we have bijection as before? And this is very, very non-trivial question. And well, there's very straightforward way how to approach this is to study Bethe ansatz equations, and well, people are doing that with into some, so you need some condition on pseudo-differential operator, so it will be in bijection with eigenvectors, right? And if you just say, okay, it's a ratio, like it's a ratio of these two with such properties, it's not enough. So you have some very non-trivial technical conditions that actually are not well understood. And so, okay, so our philosophy or our proposal is to approach. So we propose to approach this problem by interpolating GLN, well, when n goes to any complex number t. And the philosophy behind this is that when you interpolate, you actually try to grasp properties of your theory, which are universal for, so to say, all GLNs and all super Lie algebras. So actually you grasp from GLN that you can say also about super Lie algebra. And well, on one case, well, since I have 2 minutes and I still promised some Deligne categories to you, so we know how to so no monodromy condition. It actually can be interpolated, so can be interpolated to pseudo-differential operators. In a sense that, well, no monodromy condition for this for differential operator to be in this set diff op n z lambda these are just polynomial conditions on coefficients, and so we actually can end up with polynomial conditions on pseudo-differential operators, such that if I kill all in my pseudo-differential operators like this long tail, right, for all bi's where I greater than n, I get pseudo-differential operator that I need, right? Okay, so but what about the other side? Can we take our Bethe algebra and look and get something like BT where T is any C? And the answer is yes, we can. And the correct language for that is what is called the Deligne category. Okay, may I ask for another 10 minutes? Or is it would be too much?
10 minutes. Oh, no, sorry. Sorry, we have no time, Filipp. I'm so sorry.
Okay, 5 minutes.
Okay, 5.
Okay, 5 minutes. So I can just say just to these are some neat pictures. So what is this? So you take D. So this the Deligne category is the following thing. So you take RT, and the philosophy is that this is a representation theory of GLT as T is in some C. So to say. So how to construct it? Objects are words in the following letters. Well, those are just 2 letters. One is shaded dot, and the other one is empty. So sorry. So these are 2 things. And morphisms. Well, you just take, so suppose that you have one word like this, just an example, like this, and another word, f prime, say like this. And I just start like connecting them with edges. So let me just give an example like this. Say. So what I can do, I can connect by arc vertices of different kind, and by straight line vertices of the same kind. okay? And then I compose them, so composition. You just stack one morphism on top of another if you can, right? If your words match. So stacking, and then you erase loops, and multiply by t to the power number of loops. So this is composition. And then, well, this is some, after that, you you allow direct sums, and you add images of idempotence, and you get what is called the Deligne category, RT. So you add direct sums means you take additive envelope, and add images take you so the correct word is you take Karubian envelope. And well, there are objects there which correspond to well, a pair of partitions, and well, and you have actually functor from your Deligne category that takes this object to representation of GLN of weight nu, which is given by the following. It's just lambda1, lambda L, and then zeros, and then minus mu m, minus mu 1, m minus 1, and so on. So like this. So you have functor from the Deligne category to representations of GLN, and we constructed Bethe algebra in the Deligne category. Well, it's in homes of some objects there, such that this functor gives, like the image of this functor gives us the image of usual Bethe algebra. But in the same way, you have a functor from the Deligne category corresponding to n minus n prime to representation theory of GL n n prime. And actually, what we constructed this universal identity category is there is factor of it that gives you the image of super Bethe algebra. And we we proved we just proved that the relation in the Bethe algebra of the Deligne category is exactly the interpolated relations of monodromy conditions. And so therefore in super Bethe algebra you also have interpolated this interpolated conditions. So long story short, you can construct something which is easier than Bethe algebra of GLN or GLN n prime, but it grasps like something universal which is common for all of them. And this is given by interpolation. Okay, so let me finish here.
Okay, let us thank our speaker. We have to stop on the very interesting point. We are so sorry. Any comments, any questions? Anton? Maybe Anton Nazarov by chat.
Yeah, sorry, can I ask a question?
Sure.
And so I see that we have this no-monodromy condition for the superalgebra, and what is left? What we need to prove still for the superalgebra?
For the superalgebra, you need to prove. Yeah. So this is very good question. Yeah. Thank you, Anton. Well, so the thing is that what are the relations that we get if we go from the Deligne category to super algebra? right? So if you go from the Deligne category to GLN, right, then you just you have this pseudo-differential operator of order n, right, with some coefficients. But here I goes from from 0 to infinity, and so relations to go to GLN just means that you kill all BIs where I is greater than n, right, at this infinite tail, and then you end up with differential operator. So it's very interesting question how you get to pseudo-differential operator. And hypothesis is that actually you use some kind of Jacobi-Trubde identity to form like this coefficient. So BI corresponds to some transfer matrices corresponding to this diagram, column diagram. But you can form something like B lambda, right, as a polynomial in these BIs, and say that you actually kill those B lambda that go that do not fit into this hook, into this. So if you have well n here and n prime here, so you have this hook condition, right? So if your partition does not fit in there, then you kill those B lambda. And I think this is a good conjecture how you go from the Deligne category to the super case. But this is to be done.
Okay.
This is not proven.
Yeah, this is not proved.
One more.
Yes.
One more question.
Just maybe, Ras, a comment on precision. As far as I know, you try to implement the Deligne category in order to kind of proof of the bijection existence, right, in the super case.
Well, it's a long shot, but yes, that's the ultimate goal.
Yeah. So my precision is the following. I have my interest is more related to the string theoretic backgrounds, but can you? Is it applicable if I start specifying the GLN, like looking to the PSU groups or OSP supersymplectic cases? Will all this apply? Is it clear how to translate this into the Deligne formalism?
There is Deligne formalism for other groups, not GLT. I think as for now, I think you just have to start with different category. Like there's and do the same thing, right? Then you go to. I don't think if you start with Deligne category for GLT, then you get for other groups.
Yeah, that's probably what I'm anticipating. Like, are those categories known, for example, like for?
Yeah, they are known. So this is one Deligne category, which is GLN, but which has actually appeared in some example in Deligne and Milne book. I think on Tanakian categories. But then after that, why they're called not Deligne and Milne categories? Because after that, Deligne actually gave constructions of this interpolation of orthogonal group and symplectic. So I think this is where you can look.
All right, but the bijection conjecture should be translatable. This is what you state, right? Of the, I mean, you understand, of the eigenvectors into pseudo-differential operators, yeah.
Yes. I think yes. If you just repeat all of this, which is not even done for GLN, yes, I think if you repeat it for different category, right, different interpolation, then should be should give you something in other cases as well.
All right, I see. Good. Yes, thanks.
Thank you.
Okay, let us thanks our speaker again. Thank you.
Thank you very much.
Send us